Hello everyone, we are from Group 10. The topics that was given to us is Euler's equation and rigid body. We presented this video assignment for our lecturer, Dr. Rosyaini binti Afindi Zaman. Our group consists of 4 members and the first one in the group is Auni Isyamina binti Zulkifli. The second member is Nur Nabila Hanis binti Muhammad Syahrin. And the third member is Nur Tania binti Aman Shah. And the last one is Nur Fatihah binti Hanifiyah. So, what do you know about Euler's equations? Euler's equations are a mathematical equation that describe the rotational motion of rigid bodies. The equation consists of 3 differential equations. The equations are derived from Newton's second law as it applies to rotational motion. In more technical terms, Euler's equations describe the relationship between angular acceleration, angular velocity and moment of inertia of a rigid body.
Assalamualaikum, my name is Nur Tania binti Aman Shah. Today I will explain about the Euler equation. In Euler equation, the rotational motion of a rigid body is the term that describes the Euler equation of motion. This equation is derived from Newton's second law of motion applied to rotational motion. It indicates the relationship between the torques acting on the body and its angular acceleration. So, we consider a rigid body rotating about a fixed axis. The Euler equation of motion is typically written in terms of the body fixed coordinate system, which moves and rotates with the body. There are 3 Euler equations, one for each axis rotation, which is X, Y, and Z. So, as the fundamental equation governing the rotational part of the motion of any system refer to an inertial coordinate system, which is N equals to dl per dt, where N is the net torque applied and L is the angular momentum. This equation is the derivation from the rotation of the rigid body about a fixed axis, also called as the moment of inertia. As we can see in the picture, which is the rotational or the moment of inertia. So the easiest way to describe the rigid body is that in which the body is constrained to rotate about a fixed axis. So to begin with the Euler equation of motion, firstly it is explained that the rigid body L can be simply expressed when the coordinate axes are the principle of the body. So in general, we need to use a coordinate system that is fixed in the body and rotates with it in this equation. This means that the angular velocity of the body and the angular velocity of the coordinate systems are the same. So we will move on with the derivation of the trigonometric identities in Euler's equation. So firstly, in part 1, Euler's formula was used to express e power of negative I theta in terms of sine and cosine. So in the step 4, we will get the equation which is e power of I theta equals to cos theta minus to I sin theta. Secondly, in part 2, by given e power of I theta and e power of negative I theta equals to 1, in step 8, so therefore, based on the trigonometry identities, which is cos power of 2 and plus sine power of 2 equals to 1, it is proven that the trigonometry identity can be applied in the Euler's formula. So, we will move on with the application of trigonometry identities in Euler's formula. So the Euler formula has an application in many areas of mathematics such as functional analysis, differential equations, and Fourier analysis. So in this discussion, we will focus more on its application on trigonometry identities by using the Euler's formula to derive. So we will move on with the derivation of the trigonometry identities in Euler's equation. So firstly, in part 1, Euler's formula was used to express e power of negative I theta in terms of sine and cosine. So in the step 4, we will get the equation which is e power of I theta equals to cos theta minus to I sin theta. Secondly, in part 2, by given e power of I theta and e power of negative I theta equals to 1 in step 8. So therefore, based on the trigonometry identities, which is cos power of 2 and plus sine power of 2 equals to 1, it is proven that the trigonometry identity can be applied in the Euler's formula. So next, we will discuss on how to get the Euler equation of motion. So the first step is from the equation of torque, which is n equals to dl per dt. The second step is based on chapter 5 by referring to the theory of rotating coordinate system, which the rate of change of the angular momentum vector in a fixed inertial over a rotating system is given by the formula dl per dt fixed equals to dl per dt rotating plus the angular velocity times to angular momentum. So the third step is the equation of motion in the rotating system can be written as n equals to dl per dt plus the angular velocity times to angular momentum. So the dl per dt equals to angular velocity times to angular momentum. Is since L equals to I times to L, so the angular velocity can be written in the matrix rule, which is in the fifth step, and the Euler equation of motion in a rigid body can be written in the six steps.
A rigid body is a theoretical model used in physics to represent an object in which the relative positions of its constituent particles do not change over time, regardless of any external forces applied to it. It involves that the distance between the particles within the body remain fixed, and the body's shape and orientation remain constant during the rotational motion. In other words, it refers to an object that maintains its shape and size while undergoing rotational motion. The dynamics of a rigid body in three-dimensional rotation involves studying how the body moves and responds to external forces. The dynamics of the system are directed by principles such as angular momentum conservation and Euler's equation of the motion, which describe the relationship between torque, moment of inertia, angular acceleration, and angular velocity. So let's recall to Euler's equation in the context of a body constrained to rotate about a fixed axis. The first Euler's equation states that torque acting on the body is equal to rate of change of angular momentum. Next, the Euler's second equation states that the torque acting on the body is equal to the rate of change of angular momentum. And then the Euler's third equation defines the conservation of angular momentum when no external torque are present. A spinning torque is a classic example of a rigid body rotating about a fixed axis. It provides a practical scenario to apply Euler's equations and understand the rotational dynamics. So, we consider the torque is spinning with an angular velocity and experience no external torque. In this case, Euler's equations simplify because there are no external torque acting on the torque. Thus, the equations in xy z-axis is equal to 0 and the angular momentum remains constant.
So moving on to the example, so there are three questions that we got from past equation, which is June 2018 and July 2017. So for the first question, write the Euler equation of motion of rigid body at constant velocity. Second one is derive Euler equation of motion of a rigid body. And the third one is by using Euler equation, determine the net torque, which is N, of a rigid body as it rotates about a fixed axis with constant angular velocity. For solution for question number 1, which is write the Euler equation of motion of rigid body at constant velocity. So to solve this problem, you just write the Euler equation, which is N1, N2 and N3 is equal to I1 omega dot 1, I2 omega dot 2, I3 omega dot 3 plus with omega 2 omega 3 in bracket I3 minus I2 omega 1, omega 3 in bracket I3 minus I1, omega 1, omega 2 in bracket I2 minus I1 in metric form. So moving on to the solution for question 2. So how to derive the Euler equation is actually related to chapter 5 equation, which is dl over dt fixed is equal to dl over dt rotational plus weight omega cross L. So since dl over dt is equal to n, which is torque, so we can write the equation as n is equal to dl over dt rotational plus weight omega cross L. So we have to find the derivation for dl over dt rotational. So dl over dt rotational is equal to L dot, which is equal to I omega dot. So dl over dt rotational is equal to I1 omega dot 1, I2 omega dot 2, I3 omega dot 3, and we have to write the equation in metric form. For omega cross L, since L is equals to I omega, so omega cross L is equal to omega cross I omega. So since it's a cross product, then we use metric to solve this problem. And E1, E2, and E3 has been used as our unit vector. Then we got omega cross L is equals to I3 omega 2 omega 3 minus I2 omega 2 omega 3 for the first layer. For the second layer is I3 omega 1 omega 3 minus with I1 omega 1 omega 3, and the third layer is I2 omega 1 omega 2 minus I1 omega 1 omega 2. Then we factorize it. So lastly, we substitute back the equation that we got into our first equation, which is n is equal to dl over dt rotational plus with omega cross L. And at the end, we got the equation n, and we write as n1, n2, and n3 is equal to I1 omega dot 1, I2 omega dot 2, I3 omega dot 3 plus omega 2 omega 3 in bracket I3 minus I2, omega 1 omega 3 in bracket I3 minus I1, omega 1 omega 2 in bracket I2 minus I1 in metric form. For the last one, which is for question 3, so to determine the net torque, which is n, with a constant angular velocity, so to solve this problem, for the first one, we're using Euler equation. Euler equation is n1, n2, and n3 is equal to I1 omega dot 1, I2 omega dot 2, I3 omega dot 3, plus with omega 2 omega 3 in bracket I3 minus I2, omega 1 omega 3 in bracket I3 minus I1, omega 1 omega 2 in bracket I2 minus I1. So it mentioned that the angular velocity is constant, so we assume that omega dot 1, omega dot 2, and omega dot 3 is equal to 0. So for the final answer, so we got the net torque, which is n1, n2, and n3 is equal to omega cross L, which is omega 2, omega 3 in bracket I3 minus I2, omega 1, omega 3 in bracket I3 minus I1, and omega 1, omega 2 in bracket I2 minus I1 in metric form.
In summary, Euler's equations and the concept of liquid bodies are the basis for understanding and analyzing rotational motion. The Euler equation relates the angular acceleration of a liquid body to its moment of inertia and the torque acting on it. This equation allows us to study the complex dynamics of rotating objects such as torques, gyroscope, and also celestial bodies. Studying Euler's equations and rigid body behavior provides valuable insights into the underlying principles of rotational motion and allowing us to predict and manipulate the behavior of rotating bodies in a variety of real-world scenarios. That's all from us. Thank you for your time. Have a good day.